Hello and welcome to the Senior Design Expo video for the Long Range Endurance Platform Project Structures team. My name is Eric Anthony and I'm the team lead. With me are my teammates Ricardo Chaparro, Evelyn Cortez, Abigail Laguna, Hugo Montanez, and Cristian Vera. We want to thank our client, the Aerospace Corporation, for making this project available to us, and to our advisors Stephen Felszeghy and Ramon Garcia for helping us to execute it. You can see here our agenda for the presentation and how it's going to be laid out. This will be popping up between each section. What is this project that we've been working on for the last year? The Long Range Endurance Platform is a hybrid power UAV made to be able to fly for at least 4 hours while it monitors emissions from ships entering the port of Long Beach. So what did Structures team specifically do for this project? We managed and created the CAD model for it. We ran stress analysis on the various components, and we did thermal analysis on the system as a whole. When the Aerospace Corporation gave us their original patent drawings, it gave us a number of design considerations that we knew we had to keep in mind. We needed a hybrid engine, we needed to have a ducted fan, we needed to have an internal fuel reservoir. It did not, however, include dimensions or material selections. By the time we got to the end of the fall, we had an idea for some of the dimensions. We had an inkling of what some of those material selections might look like, though the CAD model didn't reflect that. By the time we reached mid-spring, however, CAD model clearly has the various material selections that we were looking at. See, it has an engine in there. The landing gear has gotten longer. And then by the time we get to our final model, the one that we have today, there's a number of notable improvements. First, the engine has become a Wankel rotary engine compared to the two-stroke engine from before. The propeller arms have gotten longer to accommodate the longer propellers since the weight of the drone went up. And they're no longer made of that 3D printed plastic from before. We have those vibration damping mounts that hold them to the duct. And the landing gear has gotten taller and a little bit wider to account for the fact that we now have a gimbal at the bottom that holds the LIDAR and a few other sensors. Let's focus on the duct for a moment. The duct itself is made of a composite design, the polyurethane foam core, and a carbon fiber shell. This is because both of these materials are very light, carbon fiber is strong, and the polyurethane foam is resistant to all of our fuel types, which is important because it's going to be in direct contact with it. The duct itself is 24 inches across at the top, just under 20 across at the bottom. Our capacity for the fuel tank is 453 cubic inches, which is more than we needed when we were looking at the two-stroke engine, though that might not necessarily be the case for the Wankel engine. The floor of it is sloped, so that way, when we're at hover, we're still going to have fuel funneled down to where the fuel pump is, even if we're at low fuel levels. We also have 4 anti-sloshing dividers every 90 degrees. This keeps the fuel from shifting around too much and interfering with our flight. When we look at the engine mount, it's a 775 aluminum fixture, and it's held in place with these 4 threaded carbon fiber rods. Those rods actually pierce through those dividers I was just talking about. This allows us to avoid any bulky mounting systems that would interfere with the airflow in the duct. And those are held in place with nuts on the inside and outside of the duct. When we look at the top housing, the housing itself is made of a 3D printed PETG with infused carbon fibers in it and holds a number of the electronics. A ducted fan attaches to the very bottom, which you can see in that bottom left picture. It's not actually directly attached to the engine. The whole housing is attached to those propeller arms that are made of carbon fiber rods. Those are attached to the duct using vibration damping mounts. The mounts are screwed into the duct by screwing into threaded sleeves that are set into the foam underneath the layer of carbon fiber. Now, I'm going to pass it off to Cristian, who's going to talk about the landing gear and the gimbal mount designs.
Thank you, Eric. So For the landing gear, we changed the design a little bit to accommodate a few of the design choices that we made. So we decided to make the landing gear 16 inches from top to base, and this was so that we could hold the gimbal, which is held by the gimbal mount, which is attached to the landing gear. Additionally, we threaded a hole to the top, which connects the landing gear to the base of the duct, and we used an M4 by 0.7 thread. Additionally, we widened the landing gear so that it was 2.75 inches wide. And this is to accommodate the 100-pound UAV mass in total. Finally, we also we found that the safety factor of the landing gear was 53.76. Additionally, the material that we chose previously is still the material of the landing gear. It's PETG. So for the landing gear, one of the main things we wanted to focus on was not only when the landing gear was stationary and the UAV was on the ground, but also what if the UAV was to fall? We were able to make this force body diagram, which shows that the weight of the UAV is equivalent to the force, the natural force of the landing gear. And since we have 4 landing gear, we made the assumption that in a perfect world, which is how we were calculating it, that each landing gear would get a quarter of the weight. So from there, we did a stress analysis, a fall from a height, and we chose a force of 315 newtons to apply to the top of the landing gear, and we fixed the portion, the bottom portion, on the ground, because that was how that's how the landing gear was going to hit the ground. So from there, we were able to find that the von Mises stresses that were applied and were on the landing gear were 6 times 10 to the 6 pascals. The deflection that occurred was 14 millimeters, and the safety factor that we were able to calculate was 3.79. From the conclusion of this, we were able to calculate that the landing gear could withstand a fall from about 2 inches. And I'll go into the calculations of how we found that out. But I do want to note that the yield stress, or the yield strength of the PETG material that we chose is 5,230 megapascals, which shows that the landing gear would still be in elastic deformation, even though it was undergoing those von Mises stresses. So from how we calculated the 2 inches of fall, so we got that the force that we applied to each of the landing gear was 350 newtons, and that was the force we applied per leg. So since we have 4 legs from the force body diagram that I showed, we multiplied the force that we applied by 4, and we got a total of 1,400 newtons. And since we have the equation of the force impact is equivalent to the mass times the gravity times the height divided by the distance of impact, we basically just simply applied the numbers into it, so that we had 1,400 newtons is equivalent to 45 kilograms, which we changed 100 pounds to kilograms, which is more or less about 45 kilograms, multiplied by gravity, 9.81 meters per second, multiplied that by the height, which is what we're actually trying to find, divided by the distance, which we used the deflection of the system because it was an elastic deformation. And like I mentioned before, it was 14 millimeters. So we changed that into meters, and we have 0.014 meters. And from there, we found that the height that it could fall from was 0.045 meters, which is about 2 inches. So the UAV is able to withstand a fall from about 2 inches. Now for the gimbal mount. We designed the gimbal mount so that it could hold the sensor, which was connected to the landing gear, and this is the mount that we designed. We changed the mounting points. Previously, it was just held on by friction, and we changed it so that it would actually screw onto the landing gear, and this would actually create support for the landing gear as well. Currently, the current mounts to the landing gear also attach via M4 by 0.7 screws, and this is also made of PETG. Additionally, we also did a stress analysis on this, and we found that the von Mises stresses that occurred were 1.5 times 10 to the 6 pascals. The deflection was 0.67 millimeters, and the safety factor that we found was 27.26. In conclusion, the gimbal mount is plenty sufficient to hold the gimbal sensor with a high safety factor with minimal deflection. And now I'll pass it on to Hugo. Thank you.
Thank you, Cristian. So the methodology used for the stress analysis involved 6 steps. The first step was load determination, in which we would determine the loads that were going to be placed on these structures using a quasi-static analysis. The second step included material selection, in which we would choose materials that contain properties that were required by the structure. The third step included structural modeling, in which we would perform the FEA and the hand calcs necessary. The fourth step was the determination of structural integrity. in which we would analyze the deformations and the stresses. And then the fifth step included the failure modes check, in which we would determine the factor of safety and determine how safe the structure was. And the sixth step was either optimizing or redesigning the structure if needed. So the first component that we analyzed were the engine mounting arms. This table shows the material properties that were used for these rods. They are rods. The total load that will be carried on these rods is going to be 20.94 pounds, which is the weight of the Wankel engine. We assume that the weight is going to be distributed evenly. So each arm is going to hold roughly about 5 pounds. The load factor is 1. The density of the material is 0.054, which make it a very light material. The price for every 48 inches of material is roughly $19. And the elastic modulus and the yield strength are shown below, which are both very high, which make the carbon fiber a very strong material. And so when we did the stress analysis for the engine mounting arms, we had to do them on 2 different lengths. The reason for this is due to the way the engine mount was designed. In order to fit the mount inside, we had to adjust the lengths of the rods to make it fit. And so again, the material is carbon fiber. Cross section for these rods is going to be around, or it's going to be a 1/4 inch. Moment of inertia is 0.192 times 10 to the -3 inches to the 4th. And so for the rod length of 6.72 inches, the factor of safety is 8.73. And for the shorter one, it was of 12.41. And when we did the analysis, there was very minimal deflection, hardly, if any, which made them very strong candidates, which is why we decided that we were going to use the carbon fiber rods. And so the next thing that we analyzed were the wings. Here's a picture as to how the wings look. So the wings, they're 10 inches in width and they're 1 foot long, and the thickness of them is 0.04 inches. So for the wings, a material had not been chosen yet, so we decided to do a trade study to determine a material for them. The 3 materials that we came up with were PETG. We chose PETG due to its easy manufacturability. All we had to do if we were to use PETG was 3D print, and then the other 2 were chosen due to their high strength. These 3 materials are all lightweight, which is something that we want. And PETG is obviously the weakest one, and the polyurethane and the aluminum are the stronger materials. And when we applied the material to the wings, we had a wing weight of 0.311, 0.322, and 0.721. So before we made a decision on the material, we decided to do a stress analysis for each of the materials to see how each material performs. We did an analysis at 1 G of acceleration. And from the 3, the one that deformed the most was the PETG, and the one that deformed the least was the aluminum. The deformation was very minimal, if any, which is why the factor of safety is so high for both of them. It was over 15. So the load factor is 2. And so after seeing how they performed against this acceleration, we concluded that we were just going to base it off of weight. And so given that the aluminum was the highest, we eliminated that one. And due to the higher strength of the polyurethane foam, we went with the polyurethane foam, since the weight difference between that and the PETG was so low, it didn't matter. And so we went with the polyurethane foam due to its high strength and its low weight. And now I will pass it on to Ricardo Chaparro, who will be speaking about the propeller arm stress analysis and the overall stress analysis.
Thank you, Hugo. Now I will be going over the propeller arm stress analysis and overall system stress analysis. As Eric mentioned earlier, the increase in overall weight caused the arms of the central housing plate to increase from 12 inches to 21 inches. To determine the best material for the arms, a trade study was conducted. The 4 materials that were considered were carbon fiber PTG, overtuned PTG, which are 3D printing filaments, carbon fiber rods, and aluminum T-slots. The table shows the different mechanical properties of each material. In the first row, the density of each material is shown. To stay within the weight requirement, all 6 arms must weigh less than 5 pounds or 22 newtons. The 3 materials that fit under this requirement are the 2 3D printing filaments and the carbon fiber rods. In the next 2 rows, the yield strength and elastic modulus of the materials are shown. In both of these categories, the carbon fiber rods have significantly higher strength properties than the other 3 materials. In the final row, the price per arm is displayed. The only drawback of the carbon fiber rods is the price because each arm would cost $76.31. In contrast, the 2 3D filaments and aluminum T-slots cost much less. Now that we know the mechanical properties of each material, it is crucial to see how each item will perform in a stress analysis under hover conditions. In this analysis, a thrust load of 77 newtons was considered for hover flight. In design number 1, the PTG material was designed into truss-like beams where it is modeled as being fixed in the center and the concentrated load is applied on the opposite side of the beam in the vertical direction. This analysis aims to simulate the outer thrust load bending the top mounting arms. The factor of safety was relatively low for both 3D filaments since 4.68 was determined for the carbon fiber PTG and 2.93 for the overtuned PTG. Under the same fixture and loading conditions, in design number 2, the carbon fiber rods performed much better because a factor of safety of 32.22 was calculated. Under the same boundary conditions, the aluminum T-slots had a factor of safety of 10.02. Based on the trade study and performance in the stress analysis, the carbon fiber rods were selected due to their high strength properties, low weight, and high factor of safety. To determine how the UAV would perform in a vertical flight, a finite element analysis was conducted. For this model, certain assumptions had to be made. The first assumption was that the UAV would be flying vertically with a load factor of 2. To do this, all 6 motors plus the central motor had to produce about 785 newtons of thrust. Torques produced from the motors were also included. The thrust and torque loads were provided by the flight subgroup. Another assumption made was that the duct had to include weight from other parts not modeled in the assembly, such as a carbon fiber shell, fuel, and other components, whose locations and fixtures were not confirmed on the duct. Furthermore, to take the weight of these parts into consideration, the weight of the duct was increased to 139 newtons. This simplification is done to account for details of the UAV that are not yet certain. The engine and other components were modeled by either concentrated or distributed loads shown in the figure as purple vectors. The large red arrow indicates that gravity is applied on the model. Finally, the maneuver created an inertial force of 392 newtons. To run the simulation, the model must be balanced by thrust, weight, and inertial forces. For this reason, the weight plus the inertial force is equal to the total thrust. There was also no net torque about the vertical axis. The figure shown here projects the von Mises stresses on the UAV with the load factor of 2. In this plot, the color scale shows red as high stress areas and blue as low stress areas. The maximum von Mises stress is located on the carbon fiber rods that attach the engine mount to the duct. The table shows a detailed stress summary of the simulation for 3 locations with the highest chance of failure. At location 1, the outer part of the top mounting plate will most likely fail from bending due to the thrust and torque produced by the motors. The factor of safety for this area is 8.38. In location 2, the weight from the engine causes stress due to bending on the carbon fiber rods of the engine mount. For this location, a factor of safety of 4.23 was determined. At location 3, the damping mount would most likely fail from tension due to the arms pulling the mounts away from the duct. This part raises the greatest concern since the smallest factor of safety was calculated at 2.12. From the stress results, the structure was able to maintain a factor of safety greater than 1.5, which means the performance requirement of the UAV. The deflection plot shown here shows how the UAV would displace at 1 g of acceleration. A maximum deflection of 2.5 millimeters is indicated on the carbon fiber arms of the top mounting structure. There is also a deflection of 1.7 millimeters on the engine mount. Since these deflections are minor, it is safe to assume that the structure will not fail due to deflection. Now I'll pass it on to Abigail.
Thank you, Ricardo. I will now go over the thermal analysis portion of the project. Given the fact that the UAV is a complex system, we wanted to find the best possible way to analyze it. In order to do this, we decided to adopt a nodal analysis approach by dividing the UAV into components and study the heat transfer relationships. Since the drone will be coated in carbon fiber, we decided to treat it as a black body with the intent of simplifying its analysis. As mentioned before, the study of the heat transfer relationships was the main focus of our analysis, given that we wanted to account for the heat generation and determine the temperature profiles of the main components. The first step of our analysis was to study the UAV's environmental conditions. Given that the drone will be completing missions at the port of Long Beach, we wanted to study the environment. More specifically, find out properties like temperatures and air velocities, with the intent of using this data for later use when determining the radiation and convection in the system. Using this data, we also calculated heat transfer coefficients for the purpose of computing the convection in the UAV using software. For the radiation component of the analysis, we used the temperature data obtained from our research to compute the radiation heat flux in watts per meter squared. The code we wrote resulted in a graph showing the radiation for average monthly temperatures. These values were later used in our thermal simulation on SolidWorks to account for the solar radiation. As mentioned previously, we wanted to perform nodal analysis. And in order to do this, we used FEA via the thermal analysis simulation feature on SolidWorks. FEA was chosen given that it is a numerical method that is useful when solving complicated geometries. And since the UAV is complex, we decided to focus on a simplified model originally created by Ricardo. On the right side is a simplified model along with other incorporated components in our analysis, like the Wankel engine, the outer propeller motors, the ducted fin motor, landing gear, the engine mount, and the sensor housing. It is worth mentioning that the thermal simulation was performed for hover only, given the flight team's calculation and data for hover mode. The engine mount has also since then been updated for a more sophisticated design, and the gimbal system incorporated as requested by the systems team. As mentioned before, the simulation was done for hover flight mode. The analysis was set up in a way that the main components were studied, provided data from the other teams. The specified powers for these components were inputted into the SolidWorks thermal simulation, as were the convection heat transfer generated by the propellers, the ambient temperature of 82 degrees Fahrenheit or 27.8 degrees Celsius, and the radiation in the form of heat flux. The values inputted for these types of heat transfer in our simulation were the result of hand calculations, Excel computations, as well as research data and data provided by the other teams in the project. As can be seen from the figure on the left, the largest temperature is present in the engine. This caused the engine mount and its attached rods to have a significant increase in temperature, given that the engine was approximated to have a temperature of around 250 degrees Celsius. The motor brackets also saw an increase in their temperature profile, which was caused by the heat generated by the outer propeller motors. Having said that, the top portion of the sensor housing temperature also increased. These results have then yielded important information into the areas of concern when the UAV is in hover mode. It is important to mention that the heat generation caused by the sensors that are expected to be mounted onto the sensor housing were not accounted for in the simulation, due to the fact that decisions were still being made about the placement of such sensors at the time the simulation was performed. And given that a simplified model of the Wankel engine was used for this analysis, further study needs to be completed on the actual CAD model, as well as its cooling system, which consists of water-cooled housing and an active cooling system in the form of oil rotor cooling. Now I will pass it on to Evelyn, who will go over the CFD analysis as well as the conclusions.
Thank you, Abigail. Similar to the FEA thermal simulation, the main goal of the CFD simulation was to find the temperatures of the main components, but taking into consideration fluid flow. The design condition that was considered for this simulation was also hover, which consists of having the ducted fan as well as the 6 outer propellers rotating at once. The angular velocities of the propellers were given to us by the flight team. The powers of the motors were also calculated and given to us by flight team. A modified engine model was used in this analysis due to shortage of time, which did not consist of the cooling system that is embedded in it. The sensors on the top housing were also not analyzed, which were due to shortage of time. Since we were not given a certain day and time that the UAV will be used, some assumptions were made. First, I should mention that the CFD simulation on SolidWorks allows you to input a location, time, and date to calculate the radiation from the sun. We assume the location to be in Los Angeles, California, and the date, June 15th, was chosen since it is the middle of the year. 2 different times of the day were used. First, 12 p.m. or noon was chosen since the sun is at its highest point at that time. The second time of the day was 5 a.m. since the side of the duct would not be hit at noon. First, I'll be speaking about the simulation at noon. As seen from the picture on the left, the solar radiation is hitting mainly the top components and not the duct. The picture on the right shows the radiation solar flux, which goes up to 1,240 watts per meter squared. It is expected for the temperatures of the top components, like the motors and their mounting arms, to be higher than those in the 5 a.m. simulation. When running the simulation, some assumptions were made. As I mentioned before, the actual CAD model of the engine was not used and the cooling mechanism was not considered. When inputting its maximum power, the temperatures were extremely high, so an assumption of 250 Celsius was made. This gave us a temperature of 239 Celsius for the engine mount. Other components that needed to be analyzed were the motors that provide power to the outer propellers as well as the ducted fan. In order to find how much the motors and their surrounding components would heat up to, the heat waste of the motors was calculated with an assumption of 80% efficiency. It is also seen that the top of the dome increased in temperature where the light blue area is, but not significantly enough where it is recommended to change the material or the model. Now, in order to consider the duct getting solar radiation, a time before sunrise was used. As seen in the pictures, the sun is mainly hitting the side of the vehicle. The solar radiation flux has a maximum value of only 487.6 watts per meter squared due to it still being early in the morning. The same assumptions and inputs previously mentioned were done for the simulation where the engine was set to 250 Celsius and the heat waste of the motors were calculated. The engine mount had a temperature of 237 Celsius in this simulation. The temperature is less than that at noon, which was expected to the sun hitting the side of the vehicle rather than the top. On the picture to the left, it is noticed that the side of the duct increased in temperature as well, but not enough to make any changes. It is noticed that the top components, like the motors and the mounting arms and its brackets, have similar temperatures at both times of the day, which means the solar radiation at noon did not make a significant impact. Now, the main reason why the CFD simulation was done was to see how the forced convection from the propellers can help in the cooling of their surrounding components. As you can see in the picture on the left, the propellers do help in the heat dissipated by the motors, but not enough to cool it completely. This is one of the motors with the highest power, which heated up the bracket up to 256 Celsius. It was expected for the propellers to be at ambient temperature, where the blue areas are, due to them rotating constantly. The ducted fan on the right shows that its motor would heat up to 361.6 Celsius, which is due to it not being subject to as much airflow as the outer propellers. Now I'll be going over the conclusions. Overall, the UAV structure was able to sustain a factor of safety of 2.12 in the stress analysis. In terms of the thermal analysis, the brackets under the propeller motors has a temperature limit of 225 Celsius, which means the brackets would melt or become soft. This will also apply for the sensor housing area where the ducted fan motor is attached to. In future work, a new material for these components should be considered, a cooling mechanism for the motors can be added to prevent the melting. Now, the structures team had a weight limit of 20 pounds. Shown in the chart, we exceeded it by 2.35 pounds, which isn't significantly high, but it can be adjusted with some changes to the materials or the sizes of some components. For future analysis, the FAA stress analysis needs to consider other flight modes with the appropriate bounding conditions. This is the same for the thermal analysis, as well as including the engine's cooling system, the sensors in the upper housing, and the gimbal system that is attached to the landing gear. This concludes our presentation. We would like to thank the Aerospace Corporation once again, as well as our advisors for their guidance.